In this lecture, we are going to solve problems related to alpha beta decay, carbon dating, and electron capture. Similarly, we will discuss the problems related to positron decay, gamma emission, okay, and furthermore. So, this is chapter number 3, and in today's lecture, we are going to solve first 10 problems, okay, of this chapter number 3, as you can see here, okay. These 10 problems we are going to solve in this lecture. So, the first problem is gallium occurs with two natural isotopes. As you know that gallium has two isotopes. Gallium 69, okay, which is 60.2% abundance in nature, whereas gallium 71, which is 39.8% in nature, having atomic weights 68.93 for gallium 69 and 70.92 for gallium 71 respectively. Okay, what you have to find, you have to find the atomic weights of that element. How you can find? So let's start. This is my solution. Okay, this is my own solution for these problems. Okay, so let's start problem number 1. As you know that the gallium 69 has a percentage of abundance 60% in nature, 60.2, whereas gallium 71 is 39.8% in nature, having their atomic weights 68.93 and 70.92. Now to find the total atomic weight, what you have to do, you have to multiply the weightage of that isotope, multiply their atomic weight, and you have to add them both. So for the case of gallium 69, this is 60.2%. So convert this percentage. So how you can convert, divide this number 60.2 divided by 100. Okay, so it gives you the weightage of this. So weightage of gallium 69 multiplies by their atomic, okay, weight, which is 68.93. Similarly, for the case of gallium 71, divide their, okay, percentage, their weightage, multiply by their atomic number, and then finally you have to sum both to find their total atomic weight. Okay. After summation sum, you will get your final results, and your final results is 69.73 AMU. Okay, atomic mass unit. So this is the atomic weight of gallium, which is 69.73 atomic, okay, AMU. So this is how you can find the atomic weight of gallium. Now let's move on towards our second problem. In second problem, it says the atomic weight of lithium is 6.941. Now the atomic weight of lithium is given, which is 69.41. It has two natural isotopes. Again, we know that the lithium has mainly two isotopes, lithium 6 and lithium 7. Okay, whereas their atomic weights are 6.015 and 7.016 respectively. Okay, what you have to find, what are the relative abundance of these two isotopes? Now you have to find their abundance. Okay, means their percentage, means their weightage you have to find. Now the total atomic weight is given, their isotopes atomic weight is given. Now you have to find the percentage, means relative abundance of both these two isotopes. How you can find? Let's move on towards our solution. Okay, so this is my solution for the second problem. So the atomic weight of lithium is given, which is 6.941. Okay, and the atomic weights of two isotopes are also given, which is this. Okay, let the abundance, because we don't know the abundance of lithium 6 and lithium 7, we have to find. So how we can find? So you have to use supposition here, you have to assume here that let the lithium 6 has an abundance of X, and the abundance of, let's suppose, lithium 7 is 1 minus X. Okay, so how you can find the weightage? Basically the total mass as we find here. You can see this is the total we find it, okay, atomic weight. But in this problem number 2, total is given. So total is equals to abundance multiplied by their atomic weight. Atomic weight is given, but abundance we have to find for lithium 6 plus abundance of this, which we assume 1 minus x, and their atomic weight, which is 7.016. So after substituting, you have to find the final value of x. So this x after finding is basically equals to 0.075. So this is basically the abundance of x as we let for lithium 6. So lithium 6 has abundance of 0.075. After multiplying by 100, you will get it 7.5%. How you can find for abundance of lithium 7? You just have to do 1 minus x, means 1 minus 0.075. Okay, you will get, okay, you will get 0.925. After multiplying by 100, you will get your final results for lithium 7 is, and that was 92.5%. So this is how you can find abundance, or you can find the total weight of some material by using, okay, their atomic weights. And by not knowing their atomic weights, you can find the atomic weights with the help of their atomic masses of isotopes. Okay, now let's move towards our third problem. So our third problem is, what minimum energy would an alpha particle need in order to react with uranium 238, okay, nucleus? So you have to find the minimum amount of energy that would an alpha particle need, okay, to react with uranium 238. So for that, it you have to react your alpha particle with uranium, okay, and the amount of energy what the alpha particle needs, okay, to react with uranium, and that is the thing you have to find in this problem. So let's start with the solution of this. So this is my solution for this problem. You have to find the minimum energy for the alpha particle to react with uranium 238. So you know that for an alpha particle to react with uranium 238, it must overcome the Coulomb barrier, because without Coulomb interaction, without Coulomb barrier, you cannot overcome to react your alpha particle with uranium. So as you know that the Coulomb energy is basically equal to Z1 Z2 E square. You can say that Q1 Q2 divided by R square, or 1 by K, and 1 by K is constant, which is equal, K is basically equals to 1 by 4 pi epsilon naught. Basically you know that E is equals to this, okay, Z1 Z2 E square divided by 4 pi epsilon naught R. This is the Coulomb's energy, okay. Whereas for the case of alpha particle, Z, you know that Z is basically the atomic number, okay. So for the case of alpha particle, the atomic number is 2, and it has to react with uranium 238. So their atomic number is 92. Okay, whereas the radius r, you already know that the radius r is basically equals to 1.2 femtometer. Okay, so radius r is nearly approaches to 1.2 femto, which is equals to 10 raised to minus 15. Okay, basically you know that the original formula is r equals to r naught a power 1 by 3, okay, femtometer. This is the original formula. R is here, R naught, which is 1.2, A power 1 by 3. But here are two things, two reactants, uranium and alpha. So A1 1 power 1 by 3 plus A2 power 1 by 3 into femtometer, which is 10 to the minus 15. Okay. After calculating, you will get, after calculating the value of R, and the final step is you just have to put your values inside your this equation, whereas you have to put 2 for Z1 and 92 for Z2. E square means 1.6 into 10 is for minus 19 square divided by 4 pi epsilon naught, which you already know the value 8.85 multiplied by 10 is for minus 12, multiplies by R, and R value you will get from this relation. You just have to put and you will get your final answer, and your final answer is basically 12.7 mega electron volts. I should write here, okay? 12.7 mega electron volts. This is your final answer for the energy, okay? Okay, so let's move towards our fourth problem. Our fourth problem says calculate the energy released when the thermal neutron is absorbed by deuterium, okay? Now you have to calculate the energy released, means total energy you have to find when a thermal neutron is absorbed into deuterium. Okay, now you have to absorb deuterium with neutron and the energy released, and that should you have to find in this problem. Okay, problem number 4. So let's move towards the solution of this problem. This is my solution. You can see because we have to absorb a neutron with a deuteron, so by absorbing this, because you know that neutron is 1 0, okay, and after this reaction it becomes a tritium with an emission of gamma rays, okay, gamma emission. So how you can find the total energy means how you can find the q value. The q value you can find is the parent minus daughter, okay. So the parent is this, okay, deuterium, and their mass you already know is 2.0018. Similarly for neutron, and you know that the mass is 1.008665, okay. Reactants minus products, and the mass of tritium is 3.0014 similarly. And with the gamma, after calculating the difference, mass defect, okay, this, and you have to multiply it by c square, means 931.502. So you will get your final q value relation in mega electron volts is 2.24, okay, mega electron volts. This is how you can find. So mass of uh, deuterium, I should write here, is basically equals to this, okay, in am joules, okay, while the mass of tritium is basically equals to this in am joule, okay. Similarly, the mass of neutron, you know that its mass of neutron is basically equals to 1.001.0080665. So after putting the values, you will get your final answer, and your final answer for the q value is 2.224 in mega electron volts. So now move towards our fifth problem. Our fifth problem is basically calculate the total binding energy of alpha particle. Okay, now you have to calculate the total binding energy of the alpha particle. How you can calculate? This is very interesting problem. You know that because you have to find for the alpha particle binding energy. So you know that alpha particle has two protons and two neutrons. The mass number is 4 for alpha particle and atomic number is 2. So after calculating 4 minus 2, number of neutron is 2. So alpha particle has 2 number of protons and 2 number of neutrons. So after multiplying 2 by mass of proton, have to add, because we have to find total mass defect, total binding energy, 2 multiplied by mass of neutron. After calculating, your mass defect is del m, okay, and finally you have to multiply it by 931, means a1 amu you already know is equals to 931.5 mega electron volts. One atomic mass unit is equals to this. So after multiplying this, you will get your final results. So you will get, let me write here, you will get your final results, and your binding energy should be then equals to this, okay. You can say 22 27.27 mega electron volts. Okay, so this is your binding energy. Okay, total binding energy of the alpha particle decay. Okay, now move on towards the sixth problem. What it says: how much energy is released when a lithium 6 atom absorbs a thermal neutron in the reaction of lithium 3 6 with an absorption of neutron decays into alpha particle and a tritium. So you have to calculate the total energy released, okay, when your lithium atom absorbs a neutron. And when lithium atom absorbs a neutron, it decays into an alpha particle with an emission of tritium. Okay, so this is the how you can find the energy released in lithium. Same procedure you have to do. Find the Q value means total energy. It is basically equal to reactants minus products into C square. Reactants is this lithium, mass of lithium minus mass of neutron. Okay, sorry, lithium, mass of lithium plus mass of neutron because this is reactant. Then minus product means minus mass of alpha, which is 4.00, okay, 86, and minus mass of tritium, which you already know, as I wrote here, 3.016049. Okay, so after calculating and multiplied by c square, you will get your final energy for this energy released in lithium. Okay, so this is how you can find the Q value means total energy. Just you have to put the values and substituting for Q. Okay, so our seventh problem is that what is the mass of lithium 6 atom in grams. You have to find the mass of lithium atom in grams. Mostly the mass is given in AMU, but what if you want to find your mass of lithium atom in grams? So to find in grams, how you can do? So this is how you can do, because we know that one basically mass is basically equals to mass of lithium is we already know is equals to this 6.015 U, and we also know that 1 U is basically equals to, okay, 1 U is basically equals to how much? 1.66054 into 10 raised to power minus 24 grams. Okay, and 1 U is equals to 1.66054 multiplied by 10 raised to power minus 27 kg. But in this problem we have to convert it into grams, so we have to multiply our mass multiplies by this value of U in grams, and this is equals to this. After multiplying, you will get your final results, and your final result is 9.99 into 10 raised to power minus 24 grams. So this is the mass of lithium in grams. Let's move towards our eighth problem. In our eighth problem, we have to calculate the average binding energy per nucleon. Now we have to calculate the average binding energy per nucleon. So for that, first of all, we have to calculate the binding energy. Then we have to calculate the average binding energy per nucleon by simply dividing nucleon by binding energy to get binding energy per nucleon. For which nuclide? Okay, for potassium 4019. You have to calculate the average binding energy for nucleon. So let's start our solution. So our solution is just simple. To calculate the average binding energy per nucleon, you just have to first calculate the binding energy. Binding energy you already know, simply calculated by, okay, by the mass defect into c square, and mass defect is simply number of number of proton multiplied by their mass of proton plus number of neutrons in that nuclide multiplied by their mass of neutron into c square. So in potassium 4019, it has 19 number of protons, and 40 minus 19 becomes 21. So 19 multiplied mass of proton plus 21 multiplied by mass of neutron multiplies by c square, and finally you will get the binding energy. After this, you have to find the binding energy per nucleon. So per nucleon you have to divide it by A, which you already know is basically the mass number. In this scenario, the our mass number is 40, so you have to divide it by 40 to calculate your average binding energy. Okay, this is how you can find the binding energy or binding energy per nucleon for any nuclide. Our ninth problem is calculate atomic weight of, okay, phosphorus 32, which is atomic weight is given, which is 31.973910. What is the value of delta, means energy, in mega electron volts? Now the atomic weight of any nuclide is given. In this case, phosphorus is given, which is 31.973910. You have to find the energy in mega electron volts. So this is how you can find the energy. Basically, you know that energy means you have to find the binding energy, okay, of phosphorus in mega electron volts. For the case of phosphorus, you know that it has, you can see the mass number is 32, but it has 15 number of protons. So number of mass number minus number of protons, 32 minus 15, you will get 32 minus 15, you will get 17. Okay, so 17 is the number of, okay, nucleus. Okay, number of proton is basically, you can say number of proton is 15, and number of nucleon is basically 32 minus 15 is 17. So what you have to do, again, first of all have to find the mass effect, then multiply by c square to get the binding energy. So mass of proton multiply by z. Mass of proton is basically, you know that 1.007825 multiply by atomic number in this is 15. So this, and here is you have to write 17 because mass number minus atomic number is getting 17 multiplied by mass of neutron, and mass of neutron you already know is 1.00865. After calculating multiply by, okay, this to convert in mega electron volts, you will get your final binding energy in phosphorus in mega electron volts is what you can calculate from this relation. Okay, so now move towards our last problem of this lecture. So our last problem of this lecture is show that 1 AMU is equals to 1.49 into 10 is per minus 10 joules. So this is very important and short problem. You just have to show that your one atomic mass unit is basically equals to 1.49 into 10 is power minus 10 joules. How you can show that? You can show that by simply using by Einstein's equations. You know that E equals to mc square, whereas mass you already know for this case is mass of proton is basically equals to 1.66 04 into 10 is to minus 27 in kg. I already told you one U means one atomic mass unit is basically equals to 1.66054 multiplied 10 is to minus 24 in grams, but 10 is to minus 27 in kg. And you know that the speed of light is 3 multiplied 10 is power 8, and E is equals to m. After putting the value of 1 AMU and c square, you will get your final answer is 1.4944 into 10 is per minus 10, which is the required results in joule of the energy. So you can say that 1 AMU is equals to 1.49 into 10 raised to power minus 10 joules. So this is how you can find, okay, to show that your AMU in joules is equals to 1.49 into 10 is power minus 10. Okay, because you know that the unit of mass is kg, and here the unit is mass per meter per second, means meter square per second square, so it becomes kg meter square per second square, and you know that kg meter square per second square basically equals to joules. So that's all for today. In this lecture, we discussed some nuclear tracks problems, okay, of chapter number 3 of our book, and this is my solution for the first 10 problems of chapter number 3. If you require this solution of my solution, you can just drop your mail. I should provide you, okay, via mail. And that's all for today's lecture. Thanks for watching. Stay tuned with us. We will solve more problems for this course, okay? And more lectures for this course. So, till now, stay tuned with us. Allah Hafiz.